Okay, now let's do a problem for a continuous median. In particular, let's look at fluid dynamics. So if you want to look at more details on this problem, if you look in Reddy's book on page 221, he gives a more in-depth description. Here's the physical motivation. You have this plate of length L. It's at some angle beta relative to the force of gravity. We have a coordinate system on this. X is perpendicular to the plate, Z is in the direction of the velocity, and we have some velocity gradient. No slip boundary conditions at the interface. And if you work through momentum equations, here's what you're left with. So you have a second derivative of the velocity, W. Here's a shear viscosity, and that balances with the gravitational force. So our boundary conditions are no slip at the interface. Here's my no slip. That's at the interface x equals L. At x equals 0, what we're saying is there's no zero shear stress. So as you move far enough away, the gradient here is 0 and there's no shear stress. So we define that at x equals 0. So what we want to do is solve this with one quadratic element. So this will give you an introduction on there's different ways of setting up elements. So far before this we've used linear elements. Now we're going to talk about a quadratic element. Now I'll go through in a minute why we do that and how it's different than a linear element. Theoretically, the solution of this has this form. So my velocity is of course a function of gravity, density, length of the plate, the angle, and shear viscosity, and it's quadratically dependent on the distance from the plate. So this is going to motivate how we define or why we introduce a quadratic element. Turns out when you introduce this, the functional form of W is going to be a quadratic, just like our theoretical solution. Alright, so of course we introduce this quadratic element to approximate the velocity. We need to have an understanding of what that entails. What are we going to have to do to actually get this approximation of the solution based on our interpolation functions, our nodal solutions. So on a quadratic element, it's a little different than what we've seen before. Previously we just had an element with two nodes. We're defining this whole thing as the element, and this 1D element has three nodes on it. So here are your three unknowns. Define them as U1, 2, and 3. It's equivalent to W, 1, 2, and 3. So you essentially have three solutions here, and to represent that we're going to use a polynomial expansion. So this goes out to quadratic, and you need to solve for C1, 2, and 3. So at U1, this is at x1, so you just plug in x1 squared. U2 is at x2, and U3 is at x3. So we assume that these are known, so we need to solve for our C1, 2, and 3. And if you invert this, work through all the math, it's detailed in Reddy's book. If you look at equation 3.2.27 on page 116 and 17, you'll find this set of interpolation functions. One other distinction here is we're defining a local coordinate system. So if you go back in your notes, you'll find a distinction between a local coordinate and our global coordinate. So now, given this definition of interpolation functions, we can plug that back in and use our definition of the K matrix, where when we work through that ODE, we get it in a weak form, we end up with this type of form for our K matrix. So it's just a matter of taking the derivative of a quadratic equation. And similar, we have our force. So what's left over from the ODE is this term. Again, we know everything. All we have to do is integrate a quadratic function. So if you work through this, integrate over 0 to h, this is on my local coordinate, this is what the K matrix looks like. Right? And here's what my body force looks like due to gravity. Alright, so let's come back to the physical problem and our boundary conditions. So we have these three nodes, 1, 2, and 3, same coordinate system, same flat plate. We're defining the nodal velocities as u1, 2, and 3, and our flux q1, 2, and 3. So this is all over one element. These Q's are my shear stress. Okay, so one thing to keep in mind is at Q1, remember it's symmetric, there's no shear stress, there's no velocity gradient at that point. So Q1 is 0 due to symmetry in the flow. Q21 is 0 because of Newton's law, internal equilibrium. So you have equal and opposite forces. So on Q2, on one side, as you go this way, you have a force, and then to get Q2 on the other side, you're going to have this force. They're going to cancel. So internally, that's 0. Alright, so we have our K matrix that we've already found. These are unknown, some known velocities, right? Remember, U3, it's no slip, so U3 is known, it's 0. These forces are due to gravity, so those are known. And some of our shear stresses are not known. For example, we don't know what the shear stress is at the interface. We've already said these are 0. So, expanding and plugging in, this is 0, these are 0. You have Q3, U1, U2 are unknown. 3 equations, 3 unknowns. This is a little bit messier, but we can solve this. So simplifying the equations, we get it down to this form. There should be a U1 here. But working through the math, we invert and we get our solution here. And simplifying further, we can get it in this form. And I'll leave it for you to go back and take U1 and U2, and we plug back in to here. So those U1s and U2s are the same as W1, W2, and W3. If you plug that in, that better be the same